This is an example of an LCR circuit where we've got a resistor, an inductor and a capacitor, and we can measure the voltage across the resistor, the voltage across the inductor and the voltage across the capacitor. And here we've got the supply voltage, and what we discover is that the supply voltage is not equal to the sum of the three voltages around the circuit, because these voltages are out of phase. So let's have a look what they may look like. Here's an example. Here it is. We've got the voltage across the resistor, and you can see the voltage across the resistor is in phase with the current. That will always be the case. The voltage across the resistor will be in phase with the voltage over the current, because there's no capacitor or inductor effect. Remember, while we're charging a capacitor or an inductor, it inhibits the current, so there'll be a phase difference. So the voltage across the resistor is in phase with the current. The voltage across the inductor leads the voltage over the current by 90 degrees, and that's this difference here. The voltage across the inductor leads the current, leads the voltage across the resistor by 90 degrees, and the voltage across the capacitor lags behind the voltage across the resistor in the current by 90 degrees. So that's why we've got this situation here. So at time 0, the voltage across the inductor is already maximum, and the voltage across the capacitor is immediately 90 degrees behind the voltage across the current. So in order to add these, to add voltages, we've got to add vectorially. And vectorially in this situation means adding the phasors. And you can see some of the example of phasors right there, where we've got the voltage across the inductor leading the voltage across the resistor by the 90 degrees, just as it was over here, and the voltage of the capacitor is lagging behind the voltage across the resistor by 90 degrees, which we can see comparing this and this. So we've got to add them vectorially. That's why we get these equations here, and we'll make a big deal about this in just a second. So let's come back to here, adding these vectorially. This is what it looks like, and you can see it from the work you've done already, that we might have a voltage across the inductor leading the voltage across the resistor by 90 degrees, and the voltage across the capacitor lagging behind the voltage across the resistor, again by 90 degrees. So voltage across the resistor is in phase with the current in the circuit. And just a reminder too, from our version of Ohm's law, Ohm's law, remember, R equals V over I. In this case, we'll talk of V equals IR. So voltage across the resistor is equal to IR. But when it comes to inductors, we have the formula voltage across the inductor is equal to IXL, the reactance of the inductor, because remember, reactance is the impedance, the resistance of flow within an inductor. And when it comes to capacitor, the voltage across the capacitor is equal to IXC, the reactance of the capacitor. So let's look then at the addition of these. So let's imagine we've got a voltage across the inductor of this much. Let's just go for 100 volt. And we've got the voltage across the capacitor of, say, 50 volt. Actually, let's not use 50, let's use 40. 40 volt across the capacitor, and let's have 80 volt across the resistor. How do we add these three to find the voltage of the supply? So we've got 40 down and 100 up. Let's add those two together. That's equivalent to 60 up. And we've got the 80 for the resistor. So let's find the resultant. The resultant is here, and this is the voltage of the supply. And we can use Pythagoras to find, I can't spell Pythagoras, so it's somewhere there. Pythagoras, this squared plus this squared equals this squared, 3, 4, 5, and so we're going to get the voltages of the supply is equal to 100 volt. Now this is how we work out the voltage of the supply. Of course, in the circuit that we set up, we switch it on and the voltage of the supply happens, but in order to calculate it, we need to add the effect of the voltage across the capacitor, inductor, and resistor to find it. So that's how we find the voltage of the supply. And then we need to find the angle, this angle here, theta, and we can say inverse tan of theta is equal to opposite over adjacent, so it's 60 over 80. Therefore, theta is equal to 37 degrees. So let's look at this diagram. We've got the voltage across the inductor, and now we've got the supply voltage. So we can say that the voltage of the inductor leads the supply voltage by 90 minus 37 is by 53 degrees. So that's here, 53 degrees. Voltage across the inductor leads the supply voltage by 53 degrees, or we could say the supply voltage leads the voltage over the resistor, across resistor, by 37 degrees. That's this angle here. It comes back to this again. Here is in red is the voltage across the resistor, and that's in phase with the current. And we can see the voltage across the inductor leads the voltage across the resistor by pi upon 2 by 90 degrees, and the voltage across the capacitor will lag by the same amount, but will lag by that. And hopefully I've done okay. So that's going to be the voltage across the capacitor. That's why we need to add our phasors: voltage across the inductor, voltage across the capacitor, and voltage across the resistor. So let's look where we started before. We talked about the voltage across the resistor, inductor, and capacitor, and we tried to add, and we realized that because they were out of phase, we had to add by this kind of diagram here. Voltage of the inductor leads the voltage across the resistor, which leads the voltage across the capacitor. But equally, if we say the voltage across the resistor equals IR, the voltage across the inductor equals IXL, and the voltage across the capacitor equals IXC, reactance, resistance, then if we divide each of them by I, we'll end up with this diagram here, which you've seen in your work as well. XL, XC, and resistance. So in this phasor diagram, we've got the reactance of the inductor, the reactance of the capacitor, and the resistance. So these two here are the reactance, and here is the resistance. And in order to find the impedance of the circuit, that's the total of reactance plus resistance, we've got to add these vectorially again. So let's see how we would do it vectorially if we've got a reactance of 80 and that's inductive reactance, and if we've got capacitor reactance of say 20 and a resistance of 40 ohms, remember they're all ohms, how do we add these vectorially? We've got 80 up and 20 down, so that means that's equivalent to 60 ohms up, and we've got our 40 ohms resistance. So what's the resultant? The resultant of their reactance and the resistance is this here. So we can say this is the impedance Z. The impedance Z. So we can calculate again by Pythagoras, and we end up with Z is equal to square root of 60 squared plus 40 squared. So Z is equal to 72 ohm. So that's the overall impedance. And we will need to then identify this angle here, theta, and we can identify theta by tan, inverse tan of 60 over 40 equals theta, therefore theta is equal to 56 degrees. So we can say the impedance would lead the resistance by 56 degrees, but it's merely a phase difference. Yeah, phase difference. And of course, when we're drawing our diagram like this, with our inductive reactance and our capacitive reactance and our resistance, our inductive reactance equals 2 pi FL, and our capacitive reactance is equal to 1 over 2 pi FC. and we can see that as frequency increases, then inductive reactance will increase and capacitive reactance will decrease. So by changing the frequency, we can change the inductive reactance and the capacitive reactance at the same time. And so when we add these two together, we might get a resultant reactance. Remember, these two are the reactants. But if we add these two together, we may get something which is positive or negative. So we may get something like this. Supposing the inductive reactance is smaller than the capacitive reactance, then we'll have to subtract this from this and end up with this. This here then will be XC minus XL, and our resistance here. So our resultant is going to be, our resultant of reactance and resistance is going to be impedance, and we will say the impedance lags behind the resistance by this angle here, by this angle theta. Similarly, if our inductive reactance is bigger than our capacitive reactance, then subtract this from this and we will end up with this amount here, which is then XL minus XC. And if we have our resistance here, again our resultant will be this here. This will be our impedance Z, which brings us back to our equations here. To find the supply voltage, we need to find the difference between the voltage across the capacitor and voltage across the inductor, and then the voltage across the resistor. So this is just Pythagoras. And in this case here, when we look at impedance, again we find the difference between the capacitance, inductive reactance and capacitive reactance and resistance. Again, Pythagoras lets us find that, and we can find the angle again, of course, as well.